Hi everyone, my name is Nianke. Thank you for listening to my talk today. I'm going to present our paper ADORE, Differentially Oblivious Relational Database Operators. Thank you to my co-authors, including Rajesh and Yinan at CMU, Zhao at Adobe Research, Danyang at Duke, and also Shumo at P0X Labs. So today's outline, I will first introduce the motivation, and I will move to the problem definition. Then I will introduce our differentially oblivious relational database operators, and I will present our evaluation results and also discuss the future work. We encounter data leakage everywhere nowadays, including medical records, financial data, and data collected by tech giants. A natural solution now is to use secure hardware enclave for encryption. So for the SGX, the pros, including the enclave memory, cannot be accessed from outputs of the enclave. And also the data outside of the enclave will be encrypted. But there are some cons. So first, the memory access pattern leakage. So here, during the encryption of the original picture, by only observing the memory access pattern, we can still recover a lot of message from the original picture. Second is the small enclave memory, which is only 128 megabytes for now. And also it comes with a lot of performance overhead, including the SGX E-call and O-call, and also data encryption and decryption inside the enclave. A natural question to ask is, how could we overcome the memory access China vulnerabilities? The previous solution is a fully oblivious algorithm. We define an algorithm A is oblivious if for any two databases D1 and D2 of the same size, and any subset of possible memory access patterns S if they satisfy the following inequalities. We say the algorithm A is fully oblivious because from the adversary's view, the memory traces on D1, D2 are indistinguishable by a negligible parameter delta here, and ensures that Entrust database host server should not be able to use the memory traces during execution of A to distinguish between any databases D1 and D2 of the same size. Then, how can we relax the fully oblivious guarantee notion here? Because it's a very strong guarantee. Previous oblivious database like OrbitDB, it has more than 100 times slower than Spark SQL. Before introducing our solution, so I will first discuss our threat model. We have similar threat model with OrbitDB. We want to outsource our database to the untrusted cloud, but the SGX enclave is trusted. The query client and also the communication is trusted. We want to protect against a potential very strong adversary, which can control the OS and or the hypervisor, except the hardware enclave. And we want to obfuscate the memory access pattern of the SGX enclave. So differential privacy is a very well understood notion. It defines that for any two neighboring database D1, D2, and all possible outputs, if an algorithm A satisfies epsilon and delta differential privacy, then it satisfies the following inequalities. So here, epsilon is an advantage of adversary observing the difference between the query answers of neighboring databases. And the delta is an addictive failure probability, which is negligible. It ensures that for untrusted clients, it should not be able to use the query results to distinguish between any two neighboring databases, D1 and D2. And then differential oblivious algorithm is inspired by differential privacy. It uses differential privacy guarantee to protect the memory traces. So we say an algorithm is epsilon delta differentially oblivious if for any two neighboring databases D1 and D2 and any subset of memory access pattern S, they are from the perspective of adversarial, the memory traces is also indistinguishable. And this indistinguishability is bounded by the differential privacy notion. So why DO makes sense? Because it's a relaxed notion of fully oblivious. The closeness only needs to hold for neighboring databases, and it allows a multiplicative, non-negligible bound e to the power epsilon. And it does not require worst-case padding like full obliviousness. And differential privacy is a theoretically sound and well-understood notion. And DO provides provable bounded privacy guarantee on memory accesses. Then we would like to introduce our differential oblivious database operator design. We introduce three operators, including filter with projection, group by with aggregation, and foreign key join. Due to time limit, I will only introduce the first two operators. So for a DO operator, we want to have a differential private oracle, which is a DP prefix sum algorithm. So in the following example, we want to know that for a length of n0 or 1 string, we can query the oracle for how many ones until the position with bounded noise s. So here in the example, the delta y2 equals to 2 plus some noise, and delta y4 equals to 3 plus some noise. And also we need some FIFO buffer, the output table, and also a recounter to implement our algorithm. So let's start for the epsilon delta DO filter. If we want to do a select from the array with a condition that the value is larger or equal than 10, we first read a batch of 4. And after checking the condition, we found that there are two tuples match the condition. And we query the oracle. We obtain the value delta y4. Then we write some tuples until the output size is delta y4 minus s. Then we read the second batch, and we write some tuples until the output size is delta y8 minus some s. Finally, we write some tuples until the output size is delta y12 minus s. And in the end, we write all the tuples left in the buffer and fill the output with dummy tuples until the output size is delta y12 minus plus s. Then the number of dummy tuples is delta y12 plus s minus y12. And this is a relatively small amount number of dummy tuple we write. The second one is the epsilon delta DO hash group by. We introduce the first practical DP distinct count algorithm. We first run a run to get the estimated number of distinct groups delta G. We will need a pseudo-random function h to map the input into a range between 0 and 1. Suppose the maximum SGX capacity of group stats is n, then we will know the number of estimated scan runs. Let's start acting. Suppose we want to obtain the average value of column 1 from the array grouped by column 2. We first run the first run to obtain the estimated number of scan run, which is k. Suppose in the ith run, we will process the tuple only if the ht is between the range I divided by k and I plus 1 divided by k. And suppose within the enclave, the stats table already contains this group. We will simply update the group. And if not, we will insert the new group value into this aggregation stat table. Then at the end of the ith run, we will write all the aggregation stat table from the enclave into the output. And we will write some dummy to fill until the size of the SGX enclave memory, which is n. Now it comes to the evaluation. We will use the big data benchmark, filter, group by, and foreign key join. We compare with OrbitDB and Spark SQL. We set the epsilon as 1 and delta as 2 to the power minus 30. First, we did some macro benchmarks, the performance breakdown. We found that most of the time is actually spent on the encryption and decryption, even for now. Then for DO filter, we found that our performance is up to 4 times better than OrbitDB, but still we are more than 10 times slower than Spark SQL. For the second DO group by, we found that although we have similar performance in the smallest benchmark, but with larger benchmark with 3 million and 30 million rows, the OrbitDB will fail because the number of distinct groups exceeds the memory capacity of the SGX enclave. And still, we are still very slower than the plain text Spark SQL, which means we have a long way to go. The final one is the DO foreign key join. Compare with OrbitDB, we are still around 7 or 8 times faster. And compare with Spark SQL, still we are still 100 times slower on the larger benchmarks. We also did some profiling on the time spent on the Python. So as you can see, as the data set goes larger for our DO operators, the time spent on dummy tuple paddings is lower. But still, for the DO foreign key join, the time spent on padding increases. This is because in DO foreign key join, we need an oblivious sort, and within that oblivious sort, we need to do a lot of padding. And currently, we do not have a differentially oblivious sort to integrate into our foreign key join, which is another future work too. To summarize, we discovered the right metrics for SGX-based data process algorithm. Then we designed several major DO relational database operators. Third, we implement DO database operator which outperform OrbitDB up to 7.4 at times on big data benchmark. For future work, we want to do some query optimization and SGX IO cost model. And also, it will be good for the differential oblivious composition for complex queries to make it practical. Thank you. And I'll be waiting for your questions.